for today wasn't going to happen. So we will get through squeeze theorem. We're going to save trig limits for the very beginning of next class. Which remember how I originally was going to give you guys a quiz next class on 1.2, 1.3. So I ended up changing that anyways because there's a fire drill happening for tomorrow and whatnot. Anyways, so what's going to happen is you'll have 1.3 practice, like the problems that you're learning today, to complete from the worksheet. So those numbers. Next class we will finish trig limits. You'll have some time to do that practice. We're going to move on to section 1.4, and then you're going to have a take-home quiz for 1.2 and 1.3, which actually lines up with last year's group anyway. So like how I did things, and that works fine. So remember, do you guys remember what your homework was that's due today? Did we do that? Can we remember what we were doing?
Yes. Okay, let's see. Is this you guys? This is you guys. Okay, cool. We got through RatCon. So if you remember, we were evaluating limits. Remember our go-to strategy when you are presented with a limit is to do what? Try what? Direct substitution. So you try plugging in whatever it is that x or the variable is approaching into the expression that represents the function, and you see if you get a number, okay? If you run into 0 over 0, which we refer to as what do we call 0 over 0? An indeterminate form. Then you know that you have more work to do, and that's what we were ending last class with, right? Like we have the different algebraic strategies where we're trying to get rid of the common factor in the numerator and denominator that's causing the 0 over 0 to see if the limit exists or not, because the limit could still not exist, but if the function actually has a removable discontinuity at whatever that x value is that x is approaching, then the limit would exist. Okay, so we went through, like with rational functions, where our strategy was FOTO, factor and divide out. We went through RatCon, right, where you're trying to rationalize either the numerator or denominator by multiplying by a version of 1 that is the conjugate of whatever you're trying to rationalize. The next strategy that can be used is whenever you have a fraction that has complex fractions. Complex fractions, what are those? Yeah, if you have a fraction in the numerator or the denominator. So, like for example, this limit here, if we plug in 0, like we try direct substitution, do we see that we'd run into 0 over 0? Do we see it? See it? Yeah. Now, because when we plug in 0, we end up with the 0 over 0, we know that the factor we're trying to get to cancel is x. If it was like as x approaches 2, and we end up with 0 over 0, we know that x minus 2 is the common factor that's causing that 0 over 0 when we're trying to get to cancel. So like for this particular limit, we know that this x that's in the denominator is the factor that we are trying to get to cancel. Now LCM over LCM. LCM refers to the least common multiple of the denominators of the complex fractions. Now, there are other ways that you could simplify and get rid of the complex fractions. Like you could think about getting a common denominator and like then doing the division with the fractions. But that's not going to be the most efficient method. Using this would be the most efficient method. Remember, like time is important. You want to make sure that you're being efficient. So you're figuring out a version of 1 to multiply by that will
cancel the complex fractions. This strategy is used when there are complex fractions. So, looking at the denominators of the complex fractions, 4 and the quantity x plus 4, the least or the smallest common multiple of 4 and x plus 4 would be
X plus 4 times 4.
x plus 4 times 4, which we're going to leave in factored form. So that means that we're going to multiply by 4 times x plus 4 over 4 times x plus 4. Remember, you have to multiply by a version of 1. You can't just multiply by 4 times the quantity x plus 4. Common mistake I'll see are people just multiplying by 4 times the quantity x plus 4, but then magic happens and somehow it still ends up working out. It can be helpful sometimes to put grouping symbols around like your big numerator and denominator to help you with thinking about distributing. Today we're really going to make sure that we are paying attention to the limit notation and using it appropriately. So, all of this is the argument of the limit right now. We still need to have the limit because the limit notation should be there until you use direct substitution again. So thinking about distributing the 4 times the quantity x plus 4 to the fraction 1 over x plus 4, do we see that the x plus 4s would cancel, leaving us with 4? Okay, minus, and then when we distribute to the 4 times the quantity x plus 4 to the 1/4, the 4's cancel, and that'll leave us with minus the quantity x plus 4. No need to multiply out the denominator. Again, we know that that x is what we're trying to get to cancel. I think some of you from here could do the simplifying and then just go directly to the direct substitution. That's fine. I'm going to write out the extra algebra steps for those of you that it might be helpful for. But again, like you can show less algebra steps, okay? So I would think about simplifying the numerator by distributing that negative. The 4's will cancel, and then now we can see that this x will cancel with this x. Again, from here you could have shown this step, and then you could go to direct substitution. I am going to show with the limit notation the simplified expression that represents the rule for the function that we're taking the limit of. And then it's here. Now when I go to plug 0 into x to see if the limit exists or not, I am dropping the limit notation. So I'll have negative 1 over 4 times 0 plus 4. This step doesn't need to be shown either. You can go directly to negative 1 over 16. Now, if you run out of room for vertical steps, here's what you can do, especially because I went kind of into the limit that's below it. Just draw a vertical line and continue your vertical steps on the other side of the vertical line. You don't need to draw a big arrow. So if this were to happen, like a free response question, you're showing your vertical steps for whatever the problem is that you're trying to solve. You just draw a line and then you continue on with your vertical steps. Like it.
Do they have to be vertical steps?
Yes. communicate your math. That would be like me asking you, can I write all the words vertically for a sentence? But why? You just can't, right? All right, so in your, let's just go with the groups you're sitting in. So U3, U3, U2. Go ahead and try this one together. Face each other. Talk about what version of 1 you're going to multiply by. Well, I guess first talk about like what your first strategy would be. And then going through it, check each other's notation. Make sure you agree with the notation that each of you is using.
So what do you guys want to multiply?
So would you guys multiply what?
Yes.
6 times x minus 6.
No, 6.
What? Oh, oops. Yeah. 6 is going to be what is
You're correct.
And he said, hold on. I write kind of slow.
Oh, I forgot
No,
to do
you're
it
right.
vertically.
What?
I did it horizontally.
You're
But
right.
then, but that did not so that just means it's just not there. Oh, and it's just.
Unforgivable.
Remember, the graph of the function that you're taking the limit of will look like the simplified version of the equation. It just has the domain restrictions of the original expression.
Negative
Sledgehammer.
What? Wait.
That's a crazy word just to have on a math assignment.
Why is...
Again, some of these you won't find in a textbook, right? What?
Feels powerful.
It does, right?
Oh.
You're like,
Upside down.
what can I do here? Sledgehammer!
Why
Okay.
are these all called with weird
You
things?
got canceled this weird.
Why not? You can come up with your own names, but I bet it'll help you when you're like, or you'll get excited if you're on like your test. You're like, recon! Like, oh, what do I do here? Oh, it's recon. All right, you guys, did you all get an answer for this one that you agree on? And you checked each other's notation. Your steps might have looked slightly different, but you all should agree on notation. Did we get dun, 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 negative 36?
Yes.
Ding, ding,
Yes,
ding.
and then cancels out the this.
Okay,
But then when you substitute a 0.
so again,
The sixes get rid of
while you are
and
using
then it just becomes
algebra
6
to
times
manipulate the expression,
I got it.
Okay.
you need to still have the limit notation. You only drop the limit notation when you use direct substitution again. So you do the mental direct substitution first, or you can actually do it, but you're not leaving it as equals to 0, 0, right? And then you show your algebra within the limit notation, and you drop once you go to do the direct substitution again, when you're trying to see if the limit actually does exist or not. Okay. Now, we have talked about dealing with, when we run into 0 over 0, using like factor and divide out, Lotto. Retcon, when you're trying to rationalize by multiplying by the conjugate, or version 1 that is the conjugate. We just went through when you're dealing with complex fractions. Sledgehammer is like, okay, we look at this and we go direct substitution for H. Yeah, we'd end up with 0 over 0. Do we all see that? And we're like, can we Fado? Nope. Can we Ratcon? Nope. Can Can we LCM over LCM? Nope. Okay, so then we're like, oh man, this is just, we have to try brute force sledgehammer and just multiply everything out in combined like terms. And like, try and get, in this case, because it's when h approaches 0 that we run into 0 over 0, we know h is what we're trying to get to cancel, right? Like this h is what we're trying to get to cancel. So, we go ahead and we're like, still have limit here. Make sure you don't switch the variables. X plus h, that quantity squared, please don't say that's x squared plus h squared. You'll make me sad. X squared plus 2xh plus h squared minus x squared all over h. And then here's our sledgehammer. Cross out what cancels. Now you could do this in fewer steps. I'm going to show the simplifying. After the x squareds cancel, you're looking at like what you have left. We know we're trying to get this h to cancel, so you're like, what algebra do I have in my toolbox? Like, what could I do? Factor out an h. Because h is the GCF of the numerator, of what's left in the numerator, right? And then you're like, oh, hey, h and h can cancel because h divided by h is 1. So now we're ready to use direct substitution. I drop the limit, and this just ends up being 2x. Boop, boop. All right, in same groups, go ahead and sledgehammer the next one. Talk to each other about how you are sledgehammering. You guys, what are those things that people light to make, not a candle, but what are the things that people light to make it smell?
Incense.
It smells like incense. Does anyone else smell that?
Incense has various smells.
Yeah.
But I feel like I can smell the toastiness of the
Okay,
incense.
probably.
The fire.
Your coffee smells like incense?
No, it's just like coffee smells toasty.
Can I smell your coffee?
What flavor is your coffee?
Coffee flavor? Smells like coffee.
But what do you have in it? Do you have like a flavor in it?
No, it just smells like coffee.
No, I don't think it's that.
Smoky-ish, I guess.
Maybe there's a fire outside.
Maybe it's
Oh,
a
yeah.
mixture. It could be a mixture of smells.
Maybe the world is on fire. The world is on fire. Yeah.
It's constantly on fire.
That's true. Maybe the world is extra on fire.
Are you referencing the Smash Mouth song?
No.
Huh?
Kind of smells like
Did you or it smelled like strawberries earlier too, and now it's maybe a mixture of coffee and strawberries?
You did your math.
No?
Low key, that's actually nice.
Math textbook. Are you an APR?
All right, Okay, you guys. Sorry, my bad.
Last year I was.
Did we sledgehammer this puppy?
Yes.
What?
Sledgehammer.
I didn't mean that. I would never sledgehammer. I would never encourage that. That was poor choice of words. I need filter.
That's hilarious.
Filter. Okay. I did not, and that's recorded too. Lovely. I would never sledgehammer a puppy or encourage the sledgehammer of puppies. I love puppies.
So you would encourage the sledgehammer to kids?
Did we sledgehammer this limit?
Yeah.
Okay, and what did we get?
2x.
2x plus 3. Fabuloso. What did I do with the... There we go. There we go. Awesome. So, we have gone through some of the different algebraic techniques that we can use to evaluate a limit when we run into that pesky indeterminate form, the 0 over 0. Okay? Now, we're going to familiarize you guys with, like, the limit of a specific type of function. We're having knowledge of this function, which again, not in a textbook, but I refer to as the Jumpman function. How many of you just had the Drake song go off in your head?
What?
Isn't there a Drake song?
Can you
Jumpman, 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 Jumpman.
There's a
Jumpman.
music case
There's no pay on time. That's okay. We can. This is important.
Sorry.
Right? Drake.
It's a song
Yeah, I
by
think that's
Canadian
not a song.
rapper Drake and American
Called
rapper
Jumpman.
Calc. That's a little bit laughing
Oh,
on
maybe.
this What a Time to Be Alive.
Okay.
It draws its name from the Nike Jumpman mascot. You listen to Drake, Miss Larissa?
You know, Drake is like my age for a record. I watched Degrassi growing up when he was on Degrassi.
Oh, really?
So there you go. See, in my head every time. Although you can also be thinking like Super Mario if you want for like this particular function. Okay, just back to that, you guys. Number one, Drake is like my age. Okay, he's a millennial. And number two, he was on this Canadian television show called Degrassi when I was growing up.
You're Canadian.
What is that show? Is it
I'm not Canadian, but it was on like the Canadian television network.
Is that reality TV?
Okay, you guys, growing up, we did not have streaming. That wasn't a thing. Netflix and stuff was not a thing. We had a limited set of TV channels, thank you, where you had to you had to know like what time things were coming on. You couldn't pause them or anything. But anyways. Yeah, it was like a popular like
I've heard a lot about it.
TV network.
I think it was popular.
It was popular. Degrassi was definitely popular. Okay, anyway. Jumpman. We actually examined Jumpman function whenever we were estimating limits numerically. Do you guys remember that one? You might have checked out the graph whenever you did that. But if we look at, or if we think about what the graph would look like, okay. Like if we think about plugging in like -3, -4, -2, -1, what would the outputs be? Like what would the y values be? -1, right? Whenever x is 0, we'd end up with 0 over 0, which are like indeterminate form. But whenever x is less than 0, the graph looks like the horizontal line at y equals to -1. And whenever x is greater than 0, the graph will look like y equals to +1. Do we see Jumpman? You could think Super Mario if you want. Don't people, hasn't Super Mario been referred to as Jumpman?
He's had many names.
Okay, well anyways, you'd have to jump. Somebody yesterday is like, well, wouldn't he have to climb? No, what is he climbing there? He would have to jump to get from the y equals -1 to the y equals to 1. It's jump man. Okay, now we could also write this function, and I'm going to get into why these two are equal to each other in a second, but we could write this function as a piecewise function, right? So y is equal to -1, like we were just saying to figure out the graph, whenever x is less than 0, or +1 whenever x is greater than 0. Now these two rules or ways of representing the rule for this function are the same because, do we remember another representation of absolute value of x? Do we remember another representation of absolute value of x? Okay, think back to when you studied rational exponents and you had to simplify expressions that had rational exponents.
Plus or minus.
No. Well, okay, let me ask you this. X could be any real number, right? But its outputs would always be positive. So what's a way using exponents that we could rewrite this statement so that it has the same domain and range?
Square root of x squared.
Thank you. Square root of x squared.
What?
The square root of x squared, right? But why? Right, because x could be positive or negative. But then remember the square root is the same as 1/2 power. So you can't just simplify that. You would want to, but you can't actually just simplify that to x because that would only be true whenever x is greater than or equal to 0, right? But for this to have the same domain and range as this, for this to have the same domain and range as this, right, we have to have those absolute value bars there. So anyways, my point being to show you that these two statements mean the same thing. If you were to rewrite the absolute value of x as a square root of x squared, think about like if you were to rationalize the numerator by multiplying by the square root of x squared over itself and then simplify, then you'd be here. And then you could just, if you kept multiplying by that version of 1, you would just keep bouncing back and forth between the two versions, right? Kind of cool, right? A little bit. Okay, anyways, either form is Jumpman. Okay, so let's think about these limits. As x approaches 0 from the left, Jumpman approaches -1. As x approaches 0 from the right, Jumpman approaches As x approaches 0, Jumpman approaches D and E. And if you were asked to justify, you could say because the limit as x approaches 0 from the left does not equal to the limit as x approaches 0 from the right. What about as x approaches 2? 1. Just direct substitution that puppy. Right? These ones, if you use direct substitution, you'd run into 0 over 0. So you do you have to think about the graph. Like you have to use your knowledge about the graph in order to determine that, hey, this is -1, this is +1. Is everyone with me so far? So this knowledge of the Jumpman function is going to allow us to think about evaluating these more complicated looking Jumpman-like functions, okay? Which is just practice with like kind of pulling out of our toolbox in order to evaluate limits. And kind of looking at functions from a different perspective. Now,
You need a graphic?
no. So we look at this. If we were to try direct substitution, do we all see that we'd run into 0 over 0? So we're like, we have some work to do. It looks, you're on like Jumpman alert because you're like, hey, it's a fraction and I have an absolute value in the numerator. You're like, can I actually uncover Jumpman here? So then looking, we're like, what algebra do we have in our toolbox that we can use to manipulate this?
Factor out 2.
Factor out 2. Now, so I'll still have limit notation. X approaches 5 from the left. When we factor out 2, since absolute value can be thought of as the square root of the quantity squared, right? Like another way to write that would be thinking about having the square root of 2x minus 10 squared. Do we see that? We can think about like exponent properties for simplifying. Like, remember how if you have a times b raised to the m power, that's the same as a to the m times b to the m? Right? Or the square root of a times b, because of that, is the square root of a times the square root of b. Cool with that? So technically, when we factor out the 2, we could think of that as the absolute value, 2 times the absolute value of x minus 5. And then the absolute value of 2 is 2. So we are allowed here, mathematically, to factor out a 2.
What if it was a -2?
But it was in the absolute value. Oh, if you factored out a -2,
Yeah,
then when you take the absolute value of -2, what's that? 2. So then it would still end up being, you could simplify it to 2. We follow that okay? Remember, absolute value represents, I'm actually teaching absolute value in Algebra 1 today. The distance of a number from 0 is the definition of absolute value. Okay, so we have uncovered Jumpman. Do we all see that? And then if you would like, I think most of you will get to a point that from here you could just think about evaluating the limit. But I'm going to show us using limit properties here. So remember that product property for limits? I can think of this as the limit as x approaches 5 from the left of 2 times the limit as x approaches 5 from the left of the absolute value of x minus 5 over x minus 5. And then we run out of space, so I'll make my vertical line. Now the limit of 2 as x approaches 5 from the left, right? 2 is just y equals to 2, constant function. That limit will be 2. What is that minus 5 doing to Jumpman? If we thought of Jumpman as being a parent function, what's that minus 5 doing? Shifting Jumpman to the right. So the jump is now going to be at 5. Well, what x is approaching has also been shifted to the right 5. So that means when we're trying to determine the limit as x approaches 5 from the left, you can just think about Jumpman having been shifted to the right 5. So that means that Jumpman would be approaching -1. Do we visualize that? The other approach you could use is when you're dealing with Jumpman and it's been shifted, you could be like, oh, I can choose a test value to the left of 5. Like if you were to plug in 4 here, wouldn't you end up with -1? Just kind of another strategy. Or Just think Jumpman shifted. Okay, why don't you guys try the next one in your group? See what you get. Now, I would be okay. I think it's okay, and I would be able to do this in my head. I think you guys could too. Is from here determining that it's -2, like going from here to be saying it's -2. That's okay. Like showing the limit property being demonstrated. Some of you, I think that's helpful for you, and if it is, do it. If it's not, and you can make the jump from there to -2, like that's cool too. Okay, see if you can figure it out. Talk to your group members. Make sure you're checking on each other's limit notation and using appropriate notation.
Me too.
I fell asleep. Woke up at 5 a.m. Accidentally fell asleep again. And woke up at
So why is it?
I woke up at 3 a.m. the first time. And then 5 a.m.
How does this happen to you?
I don't even know.
Why did you have that much
homework?
homework?
Because I fall asleep for like 5 minutes. And
Like what?
wake up
Like
again.
fucking sick?
Wait, how did you have that much work already?
Huh?
There's like, teachers are always have for next year.
It's because I had chem and bio. And I had dance.
Bio is like, yeah, that's true.
All right, you guys. Did we get it? Did we get 2?
Yeah.
Do we understand why?
Yes.
Okay, so what would we say about the two-sided limit? DNE because yeah, the one-sided limits are not equal to each other. That would be our justification here. Oops. Not so bad, right? All right, getting a little bit more complicated looking, but you're still like, hey, I run into 0 over 0. I'm on high alert for a Jumpman though. So thinking about like, well, what could you do? In the numerator, we can think about factoring a 2 out, right? And then in the denominator, we can think about factoring a 4 out. Making sure you've written down your limit as x approaches -3 from the left. Okay, I'll have 2x squared times x plus 3, or the absolute value of x plus 3, over 4 times x plus 3. So then you're like, ah, I see it. I see Jumpman there. If you want to show the limit properties being demonstrated, that's cool. You don't have to. If you see what this limit would be already. So 2x squared over 4, that's going to be x squared over 2. And then times the limit as x approaches -3 from the left of Jumpman shifted. What's that 3 doing to Jumpman? What? Left. left 3. Okay. The limit of the first of x squared over 2, right? Using direct substitution, we would get 9/2. And then what would the limit as x approaches -3 from the left be? From the left, -1. Yeah, from the left for Jumpman, it's going to be -1 unless there's been some sort of reflection that's happened. So this limit will end up being equal to -9/2. Okay, I would like the shortest person in the group to stand up and find a different group to sit with. I picked on the tall people though.
I thought you were gonna both sit.
All right, and then now go ahead and try this limit as x approaches 6 from the right.
What are we doing first?
You.
Oh.
You usually work for maybe.
So what did you guys do?
You're done?
I forgot.
Oh, okay.
It was.
And the
Okay, I'm
top.
back.
Oh, yeah. That. How'd you manage to get rid of the x minus 2?
You just pull it out.
This?
You do the thing where you,
Direct substitution.
I did that.
Oh,
Yes, me too.
You too.
I was waiting.
It hasn't even been like a full week of school yet, I'm already so drained.
honestly.
Well, maybe that means it'll adjust. Like, just.
I think it does. I think this week is like feeling hard for a lot of people. I'm feeling like it's, I'm already like treading water to, get by. I need like time to get a little bit ahead.
I have a completely new after school schedule, so I can't procrastinate like I normally do.
I'm on like a summer sleep schedule too. I mean, at the moment.
So you guys, once you've completed this one, if you've completed this one in your group, take a peek at the next one.
Would you love for schools have, if you want to apply, we will all have to know?
I hope so.
It's not all schools have.
No, I can finish the applications by the end.
Oh, yeah, that's what you said.
And then submit them when applications open, but like without favors.
Wait.
Are we still working on I, or do we have an answer for I? We have an answer for I.
What did you guys?
I is 2.
Yes.
We got 2. Okay. Next one. If you do the mental gymnastics, sure. That's one way to put it. You get 0 over 0, right, with direct substitution. So then you're like, what could I do here? If we factor 3 out of on the numerator,
And then factor the denominator. Difference of two squares. Okay, and then we're like, hey, Jumpman. Okay. Again, it's up to you if you want to show the limit properties demonstrated. So like if you wanted to show the product property for limits. I kind of like splitting up. And then we go, okay, for the first one we can try, the first factor here, we can try direct substitution. We'll get 3 times sine of 7. Someone yesterday was like, what's sine of 7? Sine of 7, right? 7's not in the unit circle. You can't simplify that. But what would the limit as x approaches 7 of this version of Jumpman be? It would be D and E. And you're like, wait. That's meaningless. That's a meaningless statement. D and E times a constant. Like that doesn't mean anything. Remember we talked about this previously? And it's kind of like red flag, hey, there's a chance this limit is D and E, but you need to investigate further. And what tools do we have to be able to investigate? We could examine the one-sided limits. We could examine the one-sided limits. So this, meaningless, means nothing. Like you would not leave your answer like this. This would not be justification for the limit being D and E. No points. Okay. So then we come over here and we're like, okay, let's, we can kind of use, if you want, you could even like copy and paste, or you could just write it out. So the limit as x approaches 7 from the left. You can reference the work that you've already done to do this, but I am writing the original limit down.
Ms. Dorset, so would the official answer just be nothing?
We're not done.
Okay.
We don't have an answer yet because what we came up with was meaningless. It just kind of gave us a, hey, you have more work to do message. So if we're thinking about from the left, you can use what you already know. So if we were to reference, like after we've used limit properties down here, but thinking about taking the limit as x approaches 7 from the left, we would get 3 sine of 7 over 14. What would the limit be as x approaches 7 from the left for that Jumpman? -1. So this limit would be negative 3 times sine of 7 over 14. And then we've considered the limit as x approaches 7 from the right. And we're like, it's going to be similar, but if we're considering the limit of Jumpman from the right, we would get +1. So this would be equal to the positive 3 times sine of 7 over 14, which is not equal to the left-sided limit. And therefore, the two-sided limit is D and E. That would be appropriate justification for the limit being D and E. So remember, I also showed you, like, whenever we ran into, remember, it was like something plus something times D and E. And we're like, okay, we have
have to investigate further. But I showed you that example, I think Alan came up with it the other day, of like where the limit actually could exist. If you pass through that. It just means you have more work to do. Or not man, a two-sided wouldn't exist though. But you can't just say that, you have to prove it. All right, questions? Before we get into squeezy wheezy theorem, thank you to all of you who did your core survey. I think everyone in here did it. Good job, guys. Not everyone did it. No, I'm not going to drop names. But everyone in here did it, which is great. The overall, for that question where I was like, what could Miss Dorset do to like support you this year? So many of you were like, give lots of time for and practice in class. I'm like, okay, yes, I will try my best. But I also want to kind of put that back on you guys. Like, I am going to give you practice for every lesson. Like, you all almost all the time have homework. You're going to have assignments over all the breaks because, like, we have so much material to get through. I know the schedule and the pace that we have to go at to get through it all. So to put it back on you, so that I'm not just assigning practice to assign practice, you need to make sure that you are approaching the practice in a productive way for your learning, okay? So like, not just doing it so that you can submit it and get your 5 points of completion credit. Like, as you're going, you should be thinking, do I actually understand what I'm doing? Could I teach this to someone else? Could I explain my thought process, why I'm doing what I'm doing in each step, right? And then if you can't do that, that's when we need to have a conversation, right? I'm a broken record at this point with it. But we have so much to get through. We're going to be moving at a really decent pace. Yes, you will always have practice. You're always welcome to look, like if you have problems assigned from the textbook, to like do extra practice, that's your choice. But again, if you're doing a ton of practice, and it's not just doing skill isn't going to work in here. Like, you need to make sure you are developing your conceptual understanding, okay? Once we get to, you need to understand what it means to take a limit. Like, what could that tell us about a function? When we get to derivatives, like, understand what a derivative is, not just how to find a derivative, but like what it is and how it could be used, right? That's how it's going to actually be useful to you. Okay, off my soapbox, unless anyone has any other questions or comments on that. No? Okay, squeezy wheezy theorem. Squeeze theorem. Also known as sandwich theorem in certain texts. Maybe countries. I don't know. Now what squeeze theorem says is, let's say we have three functions that have this relationship. So if you have three functions such that f of x is greater than or equal to h of x, so like all the function values, all the y values for the function f are greater than or equal to the y values for the function h, and all the y values for the function f are less than or equal to the y values for the function g. So if we have three functions with this relationship, that's true for all x in an open interval that contains c, except possibly at c itself. So c would be, if you're trying to evaluate a limit, right, because this is a way of evaluating certain limits analytically. So if you're trying to find the limit as x approaches c of the function f of x, and you're using squeeze theorem, okay, you have to be able, you're either given or you have to come up with this relationship for an open interval around c. But remember, for limits, how we don't actually care what's happening to the function at c. Like, it could be undefined at c. It could be defined, it could be undefined. The function value could be something different than the limit, right? So open interval that contains c. But this relationship doesn't actually have to be true at C. Does that make sense? And if the limit as x approaches C of h of x, okay, outside function, and the limit as x approaches C of g of x, the other outside function, could also think of with sandwich theorem as the bread functions, right? The bread, and then f of x would be like the inside of the sandwich. Okay. If those two limits are equal to each other, then by the squeeze theorem, the limit as x approaches C of that middle function f of x exists and is also equal to L. So here's a picture of potentially like three functions that have this relationship. Missing the inequality symbols here. Now, if you're given a limit that you can't evaluate using direct substitution, you can't use, it's not a 0 for 0 case where you could use one of the algebraic strategies we've just talked about. So you're like, is this a squeeze theorem case? The big kind of light bulb is or sign that it's a squeeze theorem limit is if you've been given this inequality about the functions. Like that's a big hey, but you're not always given that inequality. Now, if you are using squeeze theorem to evaluate a limit, you can think of it as like 3 steps, which is really the first 2 steps. You're stating the conditions for squeeze theorem to apply and be true. And then the last step in the justification is like saying like by the squeeze theorem, the limit is equal to this, okay? So 3 steps for using squeeze theorem. Okay, first one would be restating this inequality or coming up with this inequality. It's a little trickier when you have to come up with it on your own. Okay. Second is showing that the limits of the outside, the bread functions, exist and are equal to each other. And then the third is being like, oh, those 2 conditions, check. So now I can say, therefore, by the squeeze theorem, the limit as x approaches C of f of x is equal to L. You can number, I don't care if you want to number them, if you were like doing a free response, and I will give you guys free response questions on the assessment for chapter 1 for squeeze theorem. So if you want to number them, you can, you don't have to. If you want to try and like make it all flow together nicer, like by adding like, since this statement's true, and these limits are equal to this, and like add more words, like that's your call. But like bare bones, check. 1, 2, 3. Are we following this? So this is another method of evaluating certain limits analytically. Okay, so looking at this first example, this is like a super straightforward squeeze theorem. Here's the thing, I told you guys I will give you free response. Squeeze theorem usually on the actual AP will show up as multiple choice. It could potentially show up as part of a free response. I haven't seen it. But it could, I guess, right? But it will show up as multiple choice. Okay, so we are trying to find the limit as x approaches -1 of g of x. We don't even know the rule for g of x. We just know that this relationship is true. So we could restate that inequality. Find the limits of the outside functions, right? The bread functions as x approaches -1. All right, that would be 3 into the limit as x approaches -1 of that quadratic. Well, that would also be 3. So since both of those limits existed and were equal to each other, you can say, therefore, by the squeeze theorem, the limit as x approaches -1 of g of x will also be equal to 3. Okay, if you were numbering 1, 2, 3. 1 and 2 are the conditions that must be true for 3. And that is your justification. Okay. Let's do it this time. Tallest person in the group. Find a different group. Tallest person in the group. Find a different group. Okay. And then in your new groups, go ahead and try this one. Also, a classic squeeze theorem problem. Classic. Okay, so go ahead and try this one with your group. Come face each other to communicate clearly. Maybe talk to your group member. You know what ln of 1 is.
Is it 1 or 0?
Think about it.
0.
Why, maybe somebody could explain to her why it is 0.
Yeah.
What do you want theorem as TH? I forgot. Or do you want it all written down?
For theorem, yeah, I'm cool with THM.
Each of the zeros one. Anything to k on zeros one.
Thank you.
What's E again?
E is, it doesn't really matter, it's just a number.
Oh, it's a constant, right?
Like pi. Yeah, I forgot how to do ln or not. I did too. It's just.
Wait, what's ln x? It's 0,
Then
right?
you put, it's
It's
a
0?
log. So it's log of 1 equals 0. Or log of.
You guys. Log base b of, I don't know, a equals to c, right? B to the c equals to a.
Forgot.
So if you have natural log of 1, and you're like, what's that equal to? You're like, e to what power would give you 1? 0. Did you get it? And if anything, you will not forget what natural log of 1 is. Again. Right? Which is important, right? If you're trying to apply squeeze theorem, you have to know that ln of 1 simplifies to be 0. Otherwise, squeeze theorem wouldn't apply. Hey!
Did you pass?
Howdy.
Yeah, we.
Let's go. Are you driving us home today?
No. What? Yes.
Okay. Maybe the last one for today. It's 1. The limit's 1.
Yes.
Okay.
Wait, why was it?
Hey, this one.
Miss Dorset, why was it 1?
Talk to your group members for a sec.
Group, you, why would they want? Oh, sure.
The limits of the functions. You're gonna use the squeeze theorem.
What? I didn't know. Why did
I know.
Yeah, ln of x equals to 0. So, and then the x squared.
Is Ellen of anything? Why is
Wait,
Ellen
what?
X
I
zero?
thought I was gonna remember. No, ln of 1. ln of 1 is equal to 0.
Wait, why?
Because math.
ln is just log
Oh,
of
yes.
e. So e to
Each other.
Oh, it's e to the power.
Limit of
Yeah,
one
each to the power of 0.
of this
Yeah.
equation.
Oh, okay.
So this is 0 and this is 1. Log of 1 is 1.
Makes sense.
This will also the same.
Yeah.
You understand?
So it's
Except
just
this equals
1.
this equals this.
So the final equation is like this, right? And it's 1.
I'm sure I'll watch the.
Awesome.
Okay. Notice for this one, this is a limit you're presented with. Now, you wouldn't be told, hey, this is a squeeze theorem problem. Like, you would just be presented with this limit, and you're like, okay, you kind of go through your checklist. Go to direct substitution. What happens? You have 0 times sine of 1 over 0. What's that mean? I don't know. So then you're like, nope, doesn't work. Algebra? Nah. Maybe some trig identity could be applied there to where we could avoid squeeze theorem, but so this does end up being kind of a classic squeeze theorem problem, even though you haven't been, not as classic, right, as the, like, you've been given the inequality for the 3 functions. You have to figure out what the inequality is here. Okay, now x squared, well, that has a range from 0 to infinity. Okay, that's not super helpful. But sine of 1 over x, sine has a range, like the values of sine will always be between -1 and 1, right? Sine of 1 over x, it doesn't matter that the argument looks different. It is the argument and it's sine. The outputs of sine will always be between -1 and 1. So this is kind of a starting point for us, but the inequality that we're trying to come up with, like the relationship between the 3 functions that we're trying to come up with, is where that middle function would be x squared times sine of 1 over x. So do we have any ideas of how we could derive that relationship from here? I bet some of you are thinking it and you're like, that doesn't seem right.
inequality by x squared. So we'll have negative x squared is less than or equal to x squared times sine of 1 over x, which is less than or equal to positive x squared. Now, this is a really classic squeeze theorem problem. Whenever you have like a sine or a cosine, like a product with sine or cosine, since sine or cosine you know will always be between -1 and 1. You can kind of build off of there. Does that make sense? Okay, so now we have the inequality that we need, and now it's examining the limits of the outside functions, right? So the limit as x approaches 0 of negative x squared will be 0. And the limit as x approaches 0 of x squared will also be 0. Therefore, we can conclude by the squeeze theorem, the limit as x approaches 0 of x squared times sine of 1 over x is dun, 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 also 0. Right? 1, 2 conditions for 3 to hold. Is that okay? So we are going to stop here. You guys will have about 10 minutes. You can start working. Remember, you're not doing the entire worksheet yet. You're doing the problems that I put in the assignment, or you can look on the agenda. They're listed there. But you guys can have like 10 minutes to start the homework. We're going to start next class getting tricky with it, right? Doing a little trick, some trig limits. Don't worry, guys. Bring some identities in. It'll be fun. So we'll start next class with trig limits. We'll finish up 1.3. And then you guys will have a take-home quiz for 1.2, 1.3. And we will start 1.4, which is going to be, like, you're already really familiar with it, but we're just going to have, like, kind of a more rigorous definition of continuity, right? So 1.4 is all about continuity and, like, discontinuity.
Can you go back to the other problems?
Sure. I'm going to stop recording. Bye, Jack and Rose.